Last week we learned about scalars and vectors. So I want you to pause the video and make a list of those quantities which are scalars and those quantities which are vectors, especially the ones that we're looking at that we looked at last week. Okay, you're back. So under scalars, you should have written distance and speed, and you might have written some other quantities like time, mass, volume. Under vectors, you should have displacement, velocity, and acceleration. Later on, we'll see force, and later yet in the semester, we'll see momentum. Those are the 5 vectors that we'll learn about this semester. Right now we're just focused on the first 3. A scalar is a number with a unit. There's no direction associated with it. A vector is a number with a unit, but also last week had a plus or minus sign for a direction. We represent vectors with arrows. And now we're going to do 2-dimensional kinematics, but first we're going to look at 2-dimensional vectors. So we can represent these by arrows in any direction. And let's look at a displacement situation. We start at some location A. We displace, imagine that's a straight line, along the x-axis or in the east direction. Then we turn 90 degrees. We make another displacement in the northern direction. And we end up in this location. Now if we had started here and done this single displacement, these 2 displacements would be equivalent. So we could call this vector A. We'll put an arrow over the letter to indicate it's a vector B. And this would be vector C. And logically we can see that if we do A and then we do B, it's equivalent, entirely equivalent and equal to displacement C. So displacement C is equal to A plus B. And so this week we want to learn how to represent vectors in 2 dimensions and how to add them. Okay, let's go to the next page. So we represent vectors as arrows, and the length of the arrow is proportional to the magnitude of the vector, and the direction is indicated by the arrow. When we want to add vectors, graphically we add them head to tail. Now in the case of displacement vectors, it's quite logical. If you walk, say this vector, if you walk 40 meters east, 30 meters south, another 40 meters east again, then you can see graphically where you are. You've gone from here to there. And the resultant vector, the sum of those 3 vectors now, A, B, and C, would be what? Can you draw it in? Yes, you should go from your starting position to your final position. That vector, D, in this diagram, is equal to A plus B plus C. And it would be interesting to note that if you added, let's say if you added them backwards, let's add C plus B plus A. So here's, how are we going to C, B, and A. the same result. Or let's do ACB. What did we do? We did C, B, A, not to waste space. Let's do B, A, C. Same result. See these vectors? They have the same length, the same direction. Now, how would we get the length and the direction of this vector? Well, since these vectors are all perpendicular, it's easier if we do, what was this? This was C plus A plus B. You can see that that forms a right triangle. So whenever you have a right triangle, you can use the so-called Pythagorean theorem. So in this case, let's do it. The horizontal line, or this line, is 40 plus 40. Remember I said this was 40, 30, and 40. Just made those numbers up. So the C plus A means that that together is 80, and then the B is 30, and so you have a right triangle which is 80 this way, 30 that way, and you know how to get the answer. The answer for the magnitude of D, and the way we would write that is we write the vector D, and we put it absolute value signs. That means the magnitude of D. It's going to be the square root, right, because the hypotenuse squared equals the two sides squared. So it's the square root of, I'll put the numbers in, 40 plus 40, 80 meters squared plus 30 meters squared, square root. I'm going to pause the slide and get the answer. 8544. Or to two significant figures, 85 meters. Okay, now notice if we, like in the lab, we did forces. And we had a ring, and we had forces going in all different directions. And we wanted to find out force A plus force B plus force C. And we were able to add this in two ways. We added it graphically by taking, let's just say, A is a force of 100 at 45 degrees, and B is, I drew them about the same. Let's make them different though. Let's call B a force of 120, even though that's not really to scale, at, let's say that's 30 degrees below the x-axis. So measured counterclockwise from the x-axis, that would be at 330 degrees. And then we have C. Let's just say C is 80 force units. The force unit is the Newton. We haven't learned that yet, but I'll put it in there. Crowd it in here. 80 newtons. Let's say this is 30 degrees below the x-axis on that side, so that would be 180 plus 30 at 210 degrees. So this is like a force table problem, and we want to add all these vectors. So we pick a scale. We called 100 newtons 10 centimeters, and 120 newtons 12 centimeters, and 80 newtons. And then we drew them according to the angle and according to the length. So A is going to be drawn at 45 degrees. And let's see if we can get it in over here. I'll pick a length. imagine that's 10 centimeters at 45 degrees. Then B needs to be 12 centimeters, 30 degrees below the x-axis, so let me just eyeball that. A little bit longer. So there's A, there's B. I'm just doing this. Of course, if we wanted to do it exact, we'd do it with a ruler and protractor, as you did in lab. And C is 30 degrees below the x-axis and a little bit shorter than A. So let me just eyeball that. Something like this. Okay, so there's C. Now you see A plus B plus C. The sum of all those forces is this vector D. And if we were just to eyeball it, and remember this is pretty crude because I'm just going by eye, I would say that D is about the same length as A, so I'm going to say it's 100 newtons, or in lab we did in grams actually, right, because we weren't using forces. So 100 newtons or 100 grams. And it looks like it's, I can't imagine it's 30 degrees like the rest of them, but let's say it's 20 degrees below the x-axis. So at, we could say 340 degrees or minus, I'm going to say 25. I'm going to guess 25 degrees. Okay, now if I did it with a ruler and protractor, as you know, it can be very accurate. But the second way is the component method. So I'm going to go now see if I can squeeze in this component method into this slide. And if you're not familiar with this, you need to go and study because I'm going to go through this fast. Each vector A has an AX and an AY. And B, let me just let you see that. I'm putting dotted lines in. So those are the components. That AX plus AY equals A. There's a BX here, right? And a BY component. And if you add the BX and the BY, you get B back. And the same with C. CX, CY. So A has a positive X component, a positive Y component. B has a positive X component and a negative Y component. And C has a, well, I should have done the X component first, a negative X component and a negative Y component. I'm going kind of fast, but... And then we add those vectors by adding all the components. So we would make a table, the X component, the Y component, and sum them up and find the resultant vector. Now why? Because X's are in the same direction and can be added just with plus and minus signs. And the Y's are all in the same direction. So this is what we call the component method, and it's important that you learn this method. So I'm going to pause the video and do those calculations. So if you paused and got the calculations with me, these are the components of A, B, and C, and I added all the components together to get the components of D. And when I square the 105 and the negative 29.5 and take the square root, I get the magnitude of the new vector, which is 109.4. Let's call it 110. Not that far off from my very crude diagram. 110 grams or 110 newtons. And the angle would be the inverse tangent, remember that, from the equation sheet, of the y component, the negative 29.3, over the x component, the 105. And when you take the inverse tangent of those two numbers, you get an angle of 15.6, or about negative 16 degrees. I said negative 25 degrees. I don't want to make a vector. Not really that far off, considering I'm just doing it very crudely.